Recording.
What we'll go through today, we have already looked at in power systems. Okay. So in terms of your power system, we'll have different relays at different points. We have already dealt with CTs and VTs. We know where they fall in the scheme of things. Yep. So you have your CTs. Yep. Your CTs there. Of course, where we need to use VTs, we use them. But you have your CTs. The device numbers they're given. Have you accessed the list of device numbers I gave you? Were you able to find it? Because I realize I'm talking about things and I may not have published them on the site. But anyway, so we have the device numbers which are shown there, your 50 and 51, which looks to your overcurrent relays, whether instantaneous or time overcurrent relays. Yep. We're not showing, for example, the breaker numbers, which would be your 52, etc. But the bottom line is, this is the setup. You have your relays, you have your CTs connected to your relays, protecting various pieces of equipment. That's the power system. So these are the set of relay numbers that you may have. And here we are showing the PT. So you'd have your PT here. Yep. And I keep aging myself, your VTs, yes. And some of these relays, as you will see very soon, will require both inputs. So your 87, which would be your differential relay, the 87G there, your generator differential relay. We have 24. I'm just looking back at the numbers here, which would be looking at the frequency. Your 86 would be your lockout relay, etc., etc., etc. Yes. Your 21 shown there would be a distance relay. Okay, etc., etc., etc. So it depending on which relays we're using, then you would see the particular device number on your drawing. And I mean, there are quite a few numbers. You will be familiar with them with time, with use. But of course, there's no harm, there's no shame in having your manual. As a matter of fact, and I warn you against this practice because it is one that kind of pervades the industry, which is a foolish practice. I've seen it in the communications industry. What am I talking about? You have persons who declare themselves as experts if they can whether repair a system or troubleshoot a system without the manual. So you have reached expert stage when you can do the troubleshooting without the manual. There is no benefit to that, students. There's absolutely none. All right. Where necessary, get your documentation, follow your documentation, and carry out your tasks in a thorough manner. All right? You have nothing to prove to anybody in terms of what you can or cannot do. Okay? So I just want to make that clear. So if you're over time, as I said, some device numbers will become familiar. But if you are not sure, pull your list and familiarize yourself. So what we are showing here is protection that generally is used for generators. Yeah. Now, we have already given the definition for a relay, and we spoke about the fact that the changes that will occur are predetermined. So we know what change will occur based on a particular input. Okay, so once certain input conditions are satisfied, we know what the output will look like. And that is the basic principle of your relays. There's nothing, there's nothing overly spectacular about this. As a matter of fact, all the technology that we have applied to relay operation has moved it from being mechanical to mechanical in terms of its construction to using microprocessors. That's basically it. But the bottom line is it's about making predetermined decisions or having predetermined actions based on particular inputs. That's what the relay is about. So in terms of looking at relay use, relay operations within the power system, we first gonna talk about the various technologies. Look from where we have come to where we are, and then we're gonna drill down on individual relays in terms of how they operate within the power system or where they can be applied. So we'll start with the general here, then we'll go to overcurrent relays, then of course I'll take you to distance relays, etc., differential relays. And that's how we'll build out this section of the module. So for your protection relay, as the name suggests, it's about safeguarding particular pieces of equipment. And so these relays will initiate disconnection of some part of the installation. Or it may provide that warning signal. And I know it's a little difficult because you have seen this already. But for completeness, I'm going to continue with it. So in terms of the warning, as I've said before, sometimes you don't necessarily want to remove the equipment because of the level of disruption that will occur. So for your power transformer, and if we think of a relay such as the buck-Holz relay, the buck-Holz relay will send alarms based on the gases that are created within the oil or the transformer. Now, it does not mean that the fault, the winding fault that has occurred is such that it will render the transformer inoperable in a short time. And so you can live with having that relay. And maybe I shouldn't use the word live with, but we can tolerate having that alarm because we are given enough time to go into the substation, provide, whether we want to have a mobile substation. You learned about the different types of substations in power systems. We want, go in a mobile substation and bypass the one that is currently having the alarms. You with me? So by doing that, you therefore do not disrupt the electricity supply of your customers. But of course, what you do and how you respond to these faults is going to come back to the philosophy of the company, which is why protection is, in teaching protection, it's more about the concepts rather than the actual actions. Because one company may be satisfied in just going and removing, customers, tell them, oh yeah, we have a problem on this transformer, we soon get it fixed, right? But then you go to another jurisdiction and, they balk at having power outages, so they'll go the extra mile, okay? So we looked at the types of relays. You have the electromechanical, and again, you're still out of the space, but we hope we can get you in the space so you can actually touch these relays and see what they look like. So I suppose one day when you decide to come on campus, you just let me know. I'll take you into the lab and show you these devices. So, when you're making certain settings in the software, you can at least make the connection as to what you would have been doing on the relay itself. All right. So we have our electromechanical, we have our static. All right. And the static, this is the SEL, but of course, there are other static relays that are in use. It looks a little different, but you know, SEL is what we, well, the current utility uses quite a bit of them. They are good quality relays. Going back to what we also said when we looked at the current transformer. Remember, we spoke about the fact that you can make changes in terms of the burden, meaning you can change different relay or use different relay technologies for the same CT. Yeah. The electromechanical relay usually has a very high burden. And so because of the flexibility, given what we went through in that exercise, because of the flexibility of the burden impedance that you can connect to the CT, the high burden of the electromechanical, if you replace that with a static, you would not see much of a problem. You would still have much of the secondary current flowing to the relay. All right, because that resistance on that parallel path is significantly less than the impedance of the core of your current transformer. All right. So that's something we just reiterating that. So in terms of technologies, for your electromechanical, right, your attracted armature, moving coil, induction cup, thermal, motor operated, mechanical, and for, right? So we are showing here, you have some moving parts. So you have the coil, the energizing coil, yes. The current from this CTs will come through that, all right? And based on that current, you would then get a certain level of magnetic pull on the armature. Good. Once that changes, then you're moving from your pulling in. So it means that you're then going up. Good. And you're moving the normally closed and then closing the normally open. All right. Remember that these contacts are shown in their de-energized state. So the normally closed will be closed when de-energized, as we are seeing here. Yep. The normally open will be open when de-energized. Once we have energized the relay and we have operation, then the normally open will close and the normally closed will open. All right. And I'm going through all of this in a little more detail because there are some operations that we'll look at later on where all of these fundamentals will come up again. All right. So this is your electromechanical relay setup in terms of moving parts. All right. And the moving parts here help us to appreciate help us to appreciate what is happening even for the static relay. All right. You may not have movable parts, but of course you will have decision-making circuits within those relays. Here we have electromechanical, which shows a rotating disc. This was with your attracted armature. Yes. The next one would be your this would be your disc. All right, which the technology is similar to the watt hour meter, the old watt hour meter that we may be familiar with. have to respect the generation gap. But anyway, so I can't really assume that you're familiar with these meters. But yeah, it's what we used to have. And these figures, students, are in the printed material that I have already put in Schoology. So you can see better photos of them there. I also want to remind us about the time dial. We mentioned that before in terms of our brief introduction to the overcurrent relay. Yes. And the plug block, which is really a tap setting. All right. So physically, we would unscrew that plug and put it into one of those openings. Yes. And that would be our plug setting, which represents the minimum current required to operate the relay. So for your electromechanical, these things are done physically. But then when we move to the static relays, we just find other ways of achieving the same thing. All right. So if you understand these basic principles, then when we get to the static, it's just that we have now used electronics to do the same thing that we are doing on the electromechanical. It may be a little difficult to see, however, right here, right there, is where we will have the movable contact. All right. So as the disk moves, where I circle up top, that's a movable contact, and down here, that's poor. Let me see if I can find another color. I don't want to use red again. All right. So down here, that's a counter balancing spring. So when you have the relay energized for operation, then this movable contact will be brought around by the disk, which is moving the contact towards a fixed contact. All right, so there's a fixed contact behind all of this. So you can't see it, but it's somewhere back there. The disk moves, it brings it towards the fixed contact. If the condition is removed, then the spring brings the movable contact back to its rest position. All right. Now the time dial, if you recall, on the curves, you had the different time dial settings. So you had 0.5, you 1, 2, etc. Yes. All you're doing is moving this dial, and by moving the dial, you're actually moving the movable contact closer to the fixed contact. So the rest position of the movable contact is going closer and closer to the fixed contact. So when you get to 0.5, what that represents would be the smallest gap between the movable contact and the fixed contact, which is why it represents the fastest operation for your relay. So with that gap as small as it is, when you move the disk, it means that you'll close the circuit very quickly. All right, any questions? Don't tell me that that was so clear. If it's not clear, then I'm improving. All right, I will carry on.
Sir, you explained this principle last year to us, you know.
Oh, all right. So you're wasting your time then, Mr. Bokan. Is that Mr. Duncan trying to tell me?
No, sir, I'm not saying that. I'll refresh the warrant.
All right. No, we don't have time for refreshers. A long course. All right. I was just teasing. Okay. So for your static, yeah, we're dealing with microprocessors. The protective relays, in terms of what it measures and what it responds to, yeah. We're looking at voltage, current, And of course, their derived quantities, because their derived quantities, for example, power would be a function of voltage and current. Your impedance would be, again, a function of voltage and current. So one of them, in terms of the derived quantities, we're talking about a product, and then we're talking about a quotient there. Yeah. So we're dividing quantities, we're multiplying quantities. Of course, the division is a little more challenging, and we will look at that in a little more detail. Okay. So once we start looking at power and impedance, it means that we're going to have at least two inputs for those relays. So for your impedance relay, yeah, that would require both your CT input and your VT input, all right? Because those are looking at the quotient, so to speak. Similarly, anything measuring power, that too will require both inputs. Okay. So we can either look at just the magnitude of the voltage and magnitude of the current, like overcurrent relay. We also use a measure of voltage. So we look at voltage as a means of determining what the frequency on the system is like, because there's a relationship between the system frequency and the operating voltage. So we look at that voltage as a means of determining what the frequency is on the system. So as I said, in terms of the voltage and current, we're looking at magnitude, all right? And we set them based on certain thresholds and then monitor accordingly. For product, we are looking at both V and I, which is what is important. And of course, for the ratio, we are looking at V and I. All right, don't need to go into all of that right now. Okay. So we spoke about the ratio measurements, that in terms of the operation, it is basically removing the operation or disturbing a balance on the system. So under normal operations, we have them balanced. Once there's a disturbance, then we will shift the balance. And that is mechanically speaking. Yeah. But we are then able to replicate that in our static designs. So, in summary, we have the various device numbers. We have the two broad categories. We have the electromechanical, we have the static. Yes? We're looking at the different quantities that we can measure. Primarily voltage and current. That's the input that we are going to be taking. And then based on those inputs, if we are looking at just magnitude, then it means that we are either looking at just the voltage or just the current. That's for magnitude measurements. For the derived quantities, once we are going to be looking at power or impedance, it means that we are going to be using a VT and a CT. And what we said last week, because of the expense and the size for your VTs, ideally we use only one VT. So we don't replicate VTs unless, of course, the utility is awash with money and, you know, they really want full redundancy. But you hardly ever replicate VTs. And it's not only from a financial standpoint, from a technical standpoint, it's not necessary, because in terms of voltage disturbance, you're more likely to have a voltage collapse as against a transient situation where you're overshooting system voltage. And what you see, for example, the stance relay is that it operates if the impedance falls below a certain value. So even in the event that you have voltage collapse, you would still have an increase in current. So if the voltage is dropping and the current is increasing, it just means that the relay is going to operate faster because the resistance would have also fallen using the V over R relationship. All right. So just quickly, in terms of your overcurrent relay, and I'm going to switch the slides and go to another presentation, but we just look at these basic things. For your overcurrent relay, again, this is a magnitude measurement relay. So it's going to look at the current, and once the current exceeds the pickup value, then it's going to operate. All right. Otherwise, it would remain open, which means that the trip coil would not be energized. Okay. So in terms of, and this is something now, again, I'm going through a lot of these basics because it's going to come up quite often. Right? So yes, I know I did go through it before, but let's just mention it again. The CT is here. Yeah. It feeds into the relay. So what we will always show, yes, that's the relay coil, but then we'll then show the contacts. So we'll show the relay coil and the contacts separate and show where the contacts would exist. So we have there normally open contact, which means that in the de-energized state, before the relay operates, it is open. Once the relay is energized, once it goes beyond the pickup current, then the relay is going to operate. Now, of course, the assumption here is that we have an instantaneous overcurrent relay, which means that there is no consideration for the magnitude above the top current that comes to the relay. All right. And that is something that you are going to be testing in that first lab exercise. So there is a condition for an instantaneous overcurrent, yeah, which means that once the current exceeds a certain value, good, it's going to trip. But then you have timed overcurrent relay, which means that the time in which it operates, which is what you have been introduced to thus far, the time in which it operates will be dependent on the multiples of that. In other words, by what factor is the current larger than the top current? All right. So in what we are showing here, because you're not seeing any timer contact, it means that this would be an instantaneous overcurrent. Because normally what the relay, and maybe I should qualify this a bit. You remember earlier we said that the relay has predetermined output based on a certain input. We said that earlier. Yes? Now, what happens in reality is that once the relay is energized, meaning once it passes top, it's going to, you're going to have an instantaneous closing or opening of contacts. However, those contacts are then connected to a timer. And that is where you get the timing function coming in. Are you with me? So there is instantaneous closure of the relay contacts. But in terms of the full operation, it will be based on the timing that is added to that. And we'll see that in a lot more detail later on. Right? But the basic principle, we have an operating current, Once it goes above that, relay operates. Otherwise, relay remains inoperable. Okay. All right. Which is what is shown here. So you have the time delay over current relay, and that's going to respond again to a certain current magnitude. Yes. But then we build in that delay, as I mentioned. And that will be dependent on the magnitude of the relay input current. Now, you see, every time you believe we have settled on something, I go and make further adjustments to what I said. So let me give some, let me qualify some things with respect to the overcurrent relay. You do have relays where there is a specific time attached to it. All right. So you have one which is instantaneous. Once you go above threshold, it operates. You have one which has a specific time built in. But then you have a third, which is where, depending on the magnitude of the current above the top, you'll get a certain time. So if it is many times higher than the top, it will operate extremely fast. All right. The one with the time, specific time attached, really doesn't matter the magnitude above. It's going to operate in that particular space of time. Do you understand the distinction between three? So you have an instantaneous, you have one that there's an inverse relationship, and then you have one that is given a specified time to operate. All right. So this one would have an inverse relationship, meaning that in terms of the magnitude versus operating time, the larger the current, which means that the larger it is above top. Yep. It means that TD1, that time is shorter than TD2, which is shorter than TD3, because TD3, right, is closer to the top current or the pickup current. All right, so let's look now at the characteristic curves of your relays, okay? And note, it is a plot of your operating time versus multiples of top, which again, you are familiar with. Good? And we mentioned the time dial and the top setting. So the time dial setting, again, remember that dial I showed you on the electromechanical relay. Yes. So those are the different time dials, and these time dials just tells you how close the movable top in its rest position is to the fixed contact. So as the time dial number increases, what that means is that the distance between the fixed contact and the movable contact also increases. All right? So it will take longer for the disk to move the movable contact towards that fixed point. All right? And we went through that example, right? So I won't bother going over. So what we have here, in terms of the different relay characteristics, which you would have you would have, for the electromechanical, this is something that you would have plotted from empirical data. All right. So you have the CO6, which is a definite time relay, which is what I mentioned before. Okay. Meaning you have a specified time assigned for operation after it is energized. And then you have your moderately to your extremely inverse. And these relays, ladies and gentlemen, these relays are linked or used in different areas of your power network. For example, the extremely inverse, or is it very inverse? Anyway, one of them. We use them where we have fuses in the system because their characteristic is best matching the characteristic of your fuse. And so you wouldn't want to have like the CO7 operating with a fuse because in terms of timing and in terms of ensuring that there is some amount of coordination between them, you want to have the operating curves quite similar. All right. But again, don't get overly worried. We'll come back to these operations and the various calculations in detail. But I hope that we will get to some of that this evening. All right, for your impedance relays, again, they are just looking at whether or not a fault is within, falls on a particular line. Now, when we showed, let me go there. Here you have 4 transmission lines, okay? And if you note, you have you can create several zones. Don't focus on the zone that I have shown you here, because I'm going to speak about this specifically for the impedance relay. But you remember when we were talking about zones of protection, right? You would note that you would have zones overlapping. So you would have 1 to 2, that would be a zone, 2 to 4, that would be another zone. Then you have 3 to 2, and of course 1 to 3. So all these zones. Now, if I was using overcurrent relays, I want you to think about it. If I had an overcurrent relay at, say, bus bar 1, okay? And I'm using it to protect the line, you know, the line 1, 2. And let's say I had a fault at between 2 and 4. So I had a fault over here, but my overcurrent relay is here, okay? Question, for fault F, where would the fault current going to that fault come from? Let's take a stab at it. Come on, you know. Where would the fault come? It will come from both generators. Agreed? Now, yes, the next question is, if I had an overcurrent over here, which overcurrent relay would operate? And maybe if I had one here, which one would operate?
Sir, would it be B24?
That is the one you would want to operate.
Oh.
Agreed? The question is, which one will?
Sir, would all of them operate?
I don't know.
Sir,
and that is the conundrum that we're going to face. Because you would agree with me that all of them would be experiencing currents in excess of their normal operation.
Yes, sir.
Yes, Mr. Johnson.
I think it would go back to something you maybe said last year about like the rate at which they will operate. And so it wouldn't necessarily trigger all of them.
Yeah, but that may be so. And yes, I did say that, and you are correct in saying that. But let me throw a little more in the pot. Now, the fault was originally between 2 and 4, right? And what we would have loved to operate, based on what Mr. Buchanan said, and he's correct, is the relay that's handling 2 to 4. But tomorrow, we have a fault at H. Which relay are going to operate now? Again, ideally, we would love relay, the relay for line 1 to 2 to operate. What I'm driving at, students, is that whilst those are ideal conditions in terms of the relays that we would love to operate, to achieve it is extremely difficult. Because what you would have to create, you would have to coordinate this relay with this relay, with this relay, for all 3 relays to understand what would happen if you have a fault on 2 to 4, as against 3 to 2, as against 1 to 3, as against 1 to 2. Your head start here? Because you have to figure out now, when the fault is on 1 to 2, what current will 2 to 4 see? What current will 3 to 4 see, or 3 to 2 see? That's what we refer to as coordination, right? Because remember, at the core of our objective for your protection system is that we want to clear the fault with minimum disruption to customers, right? If that wasn't at the core, then it really doesn't matter. We just put in the relays, and if we need to shut down half the system every time we have a fault, then so be it. We just tell them sorry. And next day we come in the news and say, well, unfortunately, we had a disruption. I hope you didn't have anything important in the freezer. All right? But we can't do that. We're trying to maintain service. So to overcome that, that's why we use the impedance relay. And look at the beauty. These 3 boxes that you see highlighted as zone 1, zone 2, and zone 3. These are settings that we are going to put on the impedance relay, which is connected right here. If you note, all of them start from that point. So zone 1, you realize it does not go the full length of the line. Zone 1 stops here. Let me use a load up color. Zone 1 stops here. Then zone 2 stops over here. And zone 3 is all the way down here. But remember the principle that we said the impedance relay operates on? So for current, we say that if the current exceeds a certain value. For impedance, we say if the impedance is below a certain value. All right? So what we have is that when the fault occurs, if the fault occurs on line 1 to 2, up to where we have zone 1, all right? What the impedance relay will do, it will measure the impedance based on the current that is flowing into that fault. Yes, and of course the voltage, at the point. It will measure the impedance, and if the impedance falls below the zone 1 setting, it will say, aha, the fault is on the line that I am protecting, and therefore it will clear the fault. Don't worry, we'll give you some more details. Zone 2, if the fault now occurs over on 2 to 4, This relay will also see the fault. However, it will say, oh, but it's the fault is not within the zone I am protecting. It sounds like it is next door. So the fault isn't in my yard, it's in my neighbor's yard. And so like a good Jamaican, it will mind its own business, of course, depending on the parish you're living in. All right? So it will mind its own business. However, as a good neighbor, if the fault continues, you're going to intervene. You call the police and say, boy, there's something going on. So them quarreling next door, in terms of a fault, you ignore it. But if it continues, you trip. So you give them 15 minutes to quarrel. Right? But if the quarrel continues for 20, you intervene. Yeah, I know I'm talking about protection. It's all right. I guarantee you will not forget that example. All right? And then for node 3, or for zone 3, note it is not only on the next door neighbor's line. It is way down the road. So there are certain percentages that we will point out to you. All right? So, for zone 2, ideally, and the international standard is 80%. So we look at 80% of the line. And then up to zone 2, we say 120%. Then for zone 3, it's 100 plus 120%, 150% of the adjacent line. So in other words, we cast our net and we start taking care of the community. All right? So we start by looking at the neighbors. Well, first of all, we're concerned about the own yard. Yep. Then we have our immediate neighbor, and then we start looking at the community. All right? But again, we'll come back to all of that. So we call it an impedance or a distance relay. And one of the other things I want to mention here is that whilst you have one impedance relay at point X, you're then going to have one at point Y at the other end of the line looking in this direction. So this one will only look down the road. This one is looking up the road. Good? By doing that, they are overlapping. So it means that the entire road is covered. So one is looking from its rest position up to 80%. The other one is looking from its rest position up to 80%. And so in the middle, yes, you will have full protection. And of course, because they're not looking at the entire line, based on their zone 1 settings, you are going to find that we're going to need communication systems to ensure that they operate properly. Yep. So within the utility, you're going to then have your fiber network. We used to use, and if you next time you pass WOP, I can say what you might find at the other substations, but you will see a little antenna on top of the relay house, right? Small antenna. And that is what they used to use to communicate. So you used to use microwave communication. But there are some drawbacks. There are some drawbacks with microwave communication. You have to have line of sight. So in other words, the antennas had to be looking directly at each other. So transmitter and receiver had to be lined up. Huh? If that miss, you know what's going to happen. So now we have connectivity through fiber, yes, and other mechanisms. You address the already, Mr. Johnson, or is it that you get the answer?
Yeah, answered it.
Okay. So if we think now about the impedance relay, remember we said that it is based on the impedance that is measured being less than the preset value. All right. So if I have the example we have here, if you have a current that increases by a factor of 5 and the voltage collapses by a factor of 2, then the ratio will decrease by a factor of 10. All right? So you'll have the setting in terms of the current. And I shouldn't use the word setting, but the impedance plummeting by a factor of 10. And we know that 10 times the system current is very conservative in terms of current under fault. All right. Okay. So in terms of operation, it will operate if and only if the current is less than the relay setting. So we set the value of the impedance, and if the measured impedance on the system falls below that, relay operates. But as I showed you in the diagram, these relays are looking in only one direction. So in terms of what is at bus 1, it will be looking towards bus 2. All right? Now, the problem is, if that wasn't the case, if I was just looking at impedance and looking at magnitude and I had it looking in both directions, the question is, it could operate for a fault behind. Yeah? So we do have a directional element applied to your distance relay. So they are all looking in front, right? They are not concerned with what's happening behind. Of course, later on, you'll see that we have a setting that looks behind and in terms of the whole operation. And, I'm just catching up on myself and thinking that the number of things I tell you that we are going to get to, I hope you're not scared. All right, but we'll get there. We'll get there. In setting your impedance relays, we use the positive sequence impedance of the line. Right? Now, I'm telling you up front, most times when I ask a question like this, I'm going to give you everything. I'm going to give you positive, negative, and 0. But of course, I know that you know and I know that you only need the positive. So, whereas in some exams, they give you too little information, I give you the whole hog. Right? You carve off the amount of ham you want. Okay? We don't have a problem with that, right? Where's Mr. Morrison? Is he still here? I'm seeing an AJ tablet. Mr. Morrison, who names him?
That's me, sir.
I don't know who that is, sir. I don't know who that is.
Oh, that's you? Oh, that's why we're getting the feedback. So Mr. Morrison gone again. Well, I look like no fill out the add drop for him. Anyway. So for normal operations, the load current would be smaller than during a fault, and Z would be much larger. Yes. So what we're showing here is the characteristic of your impedance relay without directional element. And let me quickly point out that this is not the only representation for your impedance relay. You do have a parallelogram, yep, and that is just by virtue of your uses. So you have the offset relay characteristics, but you do have parallelogram and some other characteristics. We're not going to introduce you to all of that. What we are telling you up front, or the ones that we're going to be using is the one shown on screen. All right. So in this, what we are showing is that without the directional element, this particular relay, because the impedance because the impedance measured is less than our setting, it may trip for the fault at P1 or the fault at P3. The question is that what we want? All right. So it is looking in front as well as behind. We want to be able to determine specifically which fault it should operate for. All right. So what we have is we apply that directional element, right? So it's looking in one direction, and that's what we get. So we now get half of the circle, and it's looking in that direction. But immediately we create another problem. All right? You see this fellow here, so? That's the load impedance. Now, the load impedance, because of when we compare that to your transmission line, it has more resistance. It may have more resistance than inductance. Eh? And so you're getting it falling into the characteristic of the relay. Because remember, the relay is measuring all of this impedance. It's looking anything below that impedance, it's going to trip. The fault is below that impedance. But because of the characteristics of the load may fall within the trip circle. We don't want that to happen. So we modify this characteristic a little more. Yes. Modify it a little more. And we end up with what is a more characteristic. And that's what's MHO. Right? So it's a modified impedance relay. Yes. So ideally, remember now, let's go back. I hope I'm not making too many assumptions and going too quickly. So initially we said that the impedance must be less than the setting value, the value that I set it. Once it falls below that, it will operate. But if we're just looking at the magnitude of the impedance, then that impedance, which is measured, can be anywhere relative to the point of the impedance relay. So the relay is at a particular bus. And remember, when we speak of the relay being at a particular bus, what that means in reality, students, is that the relay is in a substation. Are we clear? So when we talk about it being at a bus, it's really in a substation. And we're looking at a line. So we may be looking at the line between Hope, which is the Old Hope substation, and the West Kings House substation. All right? If that's the case, then we will have our relay looking in both directions. And once the impedance is less, West Kings House is then connected to Boulevard. Yep. So if the relay is at West Kings House and we are using these characteristics, it will be looking on the line towards Hope and it will be looking towards Boulevard. All right? Which up of half. We say let's put in the directional element so it just look in front. So let's say we are now at West Kings House and we are looking towards the Boulevard. So that's what we would see. But because of the type of loads that we have on the system, the load impedance with its resistive component may fall within the characteristics. And we have to then make a modification to this, right? And that is what our characteristic now looks like. So note, it is looking along the line. Yes, it is looking in one direction, but now the load impedance falls outside of that. So it will not trip because it is measuring the load impedance. all right, it will only trip when the impedance of the line whose characteristic is that it is more inductive than resistive. Yep. So it means that it will be closer to the x-axis. That impedance will be closer to the x-axis. With me? As against your load impedance, which will be closer to your resistance axis. And so this is the modified characteristics, with your more characteristics for your Mr. Morris, this side for join us. This is who call him. So Morris, what is happening? You sure you want to stay in the module? Look like him put up him name and gone again. So Morrison, Trey Morrison.
So I'm here. I'm not sure why you're not hearing me.
Oh boy, you just came back.
So I've been here.
You serious? That's all. Okay, all right. Okay, so the reach of the relay, as we said, is an indication of the distance along the line for which fault detection is made. And we can use these different impedance relays just to have a longer reach. Now, here is the beauty of the static relay over the electromechanical. When you're using your electromechanical, for you to cover a three-phase line, and if you were going to look at each phase, then you'll have to have a relay per phase. So you'll basically end up with 6 on each line if you're going to monitor all 3 lines. Good? With your static relay, you have 1 relay, and you'll get the input from all 3 phases. Yeah? As a matter of fact, some of those relays gives you the option of not only distance, but overcurrent protection. So the cost for your relays is therefore much less. All right. So this would be the three impedance relays. But as I said, what we do is now to have different settings for each zone. All right? And that would be a modified Moore relay. Each of these representing an impedance for the zone. So for the zone 1, you have it as Z1. Zone 2 and zone 3. All right? Any questions? You guys scaring me. Anyway, so in terms of their operations, for your zone 1 setting, it is usually 80% reach, and it carries an instantaneous operation. In JPSCO, they use 90%. All right, but I have to prepare you so that when you go elsewhere and you see the 80%, you at least can appreciate it. So JPSCO from a company policy standpoint, in fairness, and maybe I need to double check that with them again. I know they would have changed carte blanche, but they were at 90%. All right. And I'm still trying to figure out how we're going to sort out a field trip. COVID or COVID not. Or we have to figure that one out. Anyway, I'll come back to you on that one. For your zone 2 setting, it is set at 120%. So if and you're assuming it's 120% of the line that is being protected. So if you assume that the lines are equal in length, then it means that it will go over by 20% on the adjacent line. All right? So come now, let's make it practical. I'm standing at Old Hope Road. And I am now protecting the line between Old Hope Road and Cane River. Right? Cane River is in eastern St. Andrew. Right? So I'm looking towards Cane River. That's my impedance relay, and I'm looking at the line that goes down to Cane River. Now let us say the line is the total resistance of the line is 100 ohms. All right? At 100 ohms, zone 1 setting that I would put in the relay would be 80 ohms. So that is zone 1 setting. That's 80% of the impedance of the protected line. Now, assuming that the line from, I'm trying to remember where the one from Cane River is. I think it goes into Yalas. But if the line from Yalas, from Cane River to Yalas, if they are the same length, then what we are saying is that zone 2 setting, well, it really doesn't matter, but it's 100%, 120% of the line being protected. So the impedance that you would have there would be 12 ohms. Because 120% of 10. Now, in addition to the reach, to the extended reach, you're also going to include a time delay of 200 to 300 milliseconds. Remember what I said earlier? You're going to allow the quarrel in the next door neighbor's yard to continue. Yes? For a time t. And what we are saying here, for your zone 2 setting, that time t is 200 to 300 milliseconds. And if the fault is not cleared, if you have a zone 2 fault and the fault is not cleared in 200 to 300 milliseconds, then the relay at Old Hope will operate. And what is happening here, students, and again, we're going to get into the details, but what is happening here is that the relay is giving the opportunity to the other impedance relay in Cane River to operate instantaneously. Because it senses that it's a zone 2 fault. So in other words, it's on the other line. Right? But I am oversimplifying because you also have to consider that there would be a relay at Cane River looking back at Hope so that you have the overlap. So the fact that it's zone 2 doesn't mean that it is on the adjacent line. It just means that it is beyond the 80%. But beyond 80%, you still have 20% on the protected line. All right? And we refer to that as the in zone. But don't worry, we'll come back to it. For zone 3, and this now is related to the diagram that we have. For your zone 3, it's 100% of the protected line plus. So I should maybe remove that and, but plus 120% of lines 2, 3, or 2, 4, whichever of them is longer. So it's 100% of the protected line plus 120% of the adjacent line, whichever adjacent line is longer. So you're going as far out as possible on this zone 3, which means that the delay on this is going to be even longer because you're by saying putting in zone 3 time, you're giving the protection, the impedance relay on 2 lines down the road to operate, if that is indeed where the fault is. All right. All right, I'll come back to that. We'll go through that another time. So let's just look back at what we said just now. All right. So you have the relay at point 1. All right. The zone 1 setting would be 80%. So that is 80%. The zone 2 setting would be 120% of 1, 2. Right? Wherever it falls over on the adjacent line is neither here nor there. You just know that it's 120%. For your zone 3, it's 100% of this plus 120% of either this or this, whichever of them is longer. All right. So let's tell you what. Let's go through this example. So did I go through this with you before? All right. So take the question and let's run through it. Let me just pause the recording so we don't. Okay. So I didn't add any additional slides, so I'm gonna have to write and curious. Okay, so let us say the impedance at we're looking at B12. All right, we're looking at B12. So we're looking at the relay at that point. So we're looking at line 1, 2. Let me erase that. All right, so we're at this point, and we're looking in that direction. Okay? The impedance seen at that point, or the impedance measured at that point, Z, would be equal to V over I. But remember now that this impedance is, or this current rather, and this voltage is being supplied by your VT and your CT. All right? So the actual Z that will be seen, let's call that Z prime. The actual Z that will be seen would be V over the 3000 to 1 divided by I, which is over the 1500 to 5. What do you think?
Yes, sir.
Which gives us, therefore, Z prime to be equal to Z over 10. All right? So in other words, what I am seeing at the relay would not be the actual values of the line impedance, but it would rather be a scaled replica, so to speak, based on the current and voltage values that are being supplied. So the question was for us to determine the zone settings for the relay. All right? So the first thing we need to do is to determine which of the impedances we are going to use. The protection is for B12. So it means that we are looking at line 1, 2. So that's the impedance. All right? So for the zone 1 setting, I'm just going to go to the other page. As I said, I didn't have any, because normally I would have given this as an assignment. So the zone 1 setting is going to be 80%. Yes? It's going to be 80% of Z12. All right? And Z12 is 8 plus J50. So 80% of that would be 6.4 plus J40. All right? So Z1 would be 6.4 plus J40. However, because I'm seeing this impedance through the CT and the VT, yes, the setting on the relay, Z setting, ZR1, would therefore be equal to 0.64 plus J4. It would be a tenth of what it actually is. But of course, we know by now that complex numbers is a concept, and you know we don't have an imaginary axis. That's right, go. So it means that the setting ZR1, find the modulus of this, yep, and of course the angle. So it'll be 4 point something at an angle of, and because it's a line, the angle would be somewhere 70 enough or in the, or, yeah?
So it's 4.0509 at an angle of
0.051 at an angle of
80.91.
80.91 degrees. Right? And of course, that's ohms. So the setting on the relay would be that 4.051. And then the zone 2 setting, we'd have 120% of this. So that would give us, again, 1.2 times 8, that would be 9.6. 1.2 times 50, yeah, that would give us 60. So it's 9.6 plus J60. We're dividing that by 10. Excuse me. So we get 0.96 plus J6. And of course, since we are multiplying the complex number by a constant, then the angle will remain the same. Or we could have just multiplied, well,
So the magnitude for zone 2 is 6.07. 6.
Okay? And at the same angle.
Yes, sir.
And then for the so the adjacent line, based on what we are protecting, it will be 100% plus 120 of the adjacent line, whichever is longer. So you need to determine which of the two will be longer. So the adjacent lines, the options you have would be for 2, 4. Or 1, 3. Well, that's a 1, 3 or 2, 3, sorry. So we're looking out. All right, so we have 2, 3, or we have 2, 4. So which one are you going to choose?
2, 3.
Yes, sir. 2, 3.
All right. And of course, you multiply and then you divide by a 10. All right. And that will be the setting for your impedance, really. Nice and simple.
Sir, one question before I move on. So for what we're doing, zone 3, is it zone 3? Yeah, zone 3. So we're going to add the impedance of the first line plus the 120 of the line that we choose. Okay.
Yes. All right. So in terms of setup, here is how the whole thing is done. So you have your VT input, your voltage transformer input. You have your CT input. Good. And this is shown on a static relay, really. Okay? Because all three are on the same device. The zone 1 coil, the zone 2 coil, the zone 1 coil, the zone 2 coil, the zone 3 coil. All right? Now, based on what you are seeing before you, you recognize that all three of them would experience the fault at the same time. Everybody with me?
Yes, sir.
Agree with that? Mr. Johnson, Mr. Morrison, you're with us?
Yeah, man, I'm following you completely.
Yeah. How about you, Mr. Morrison? By the way, Mr. Morrison, one to your camera. Well, I'm gone again. So Morrison, you play hide and seek with us, man. What? It's Minister 7, right? Didn't expect this thing to take so long, man. Anyway, so students, work with me now. We have the three coils representing zone 1, 2, and 3 as I've shown up at the top. Everybody comfortable with that? Now I want you to look below that. Remember what I said earlier. based on what we know of a relay, it gives a predetermined response to a particular input. Good. So what we have here is that all three coils will become energized simultaneously because it's one fault. We can't experience the fault at different times. Are you with me? So as part of the operation, what we then have are then the three instantaneous contacts. And these are your instantaneous contacts. So although I mentioned earlier that only the zone 1 setting is instantaneous, the truth is all three will have an instantaneous contact, which is, let me put those in different colors. So the instantaneous contacts, I'm putting them in blue. So we have Z2, Z3, and Z1. They are all instantaneous contacts. All right? Now, in terms of your operation, if the fault is in zone 1, which means it is on the protected line. If it is in zone 1, on the protected line, then the instantaneous contact for Z1 will close. And it will close this circuit and energize the trip coil for your breaker. And your breaker would open its contacts and the line is disconnected. You comfortable with that? The other two contacts, the zone 2 contact, the instantaneous zone 2 contact, what it does is to energize a timer, a zone 2 timer. And that's where you're now going to get the 2 or the 300 milliseconds. Similarly, T3 would be the timer for zone 3. If the 200 or 300 milliseconds passes, then the instantaneous contact from the timer will now close and close your circuit. Or if the time continues and it goes to T3, then that will close and close your circuit. So what you have here is backup protection being provided at point 1, 2. Any questions?
Yes, sir. I'm not sure if they said it. What is the?
That's an intentional delay contact. I didn't say it. It's an intentional delay where, although you have you want instantaneous operation as a result of the zone 1, you have it in place just to ensure that everything is working properly. It's an intentional delay.
That's it.
And you see its coil is up here, which it actually, this is a way of ensuring that this is a way of ensuring that the communication system, etc., is in working order. All right, let's not go into details, but it's a fail-safe type of mechanism just to ensure that the system is operating as it should. Again, we will go into details. Well, so welcome back, Ms. Gray. But as you return, Mr. Morrison disappear. We'll continue to play hopscotch. Any other questions on what I just said?
Sir, the Z2 and the Z3 that you have circled, the blue, you circle in blue. Can you just go over just one of them, just one example I want to need? Because I realize that they're connected in shunt to the power source, and to me that looks like a short circuit. So just
no, man. What they are doing? What they are doing is that they are energizing the timer. One of the things you need to bear in mind, well, I shouldn't say bear in mind because I'm supposed to tell you, right? At your substation, you must have a constant supply of power, electrical energy, right? And it is supplied by batteries. So you use a station battery. You don't rely on the utility. You rely on the utility in as far as you require it to maintain a charge on the batteries. You with me?
yes,
So you always have a station battery and you'll always see a DC source there. So when you have these instantaneous contacts, right? When they close, what they are doing, they have turned this timer on. So you may not want to consider it as just a single circuit, eh?
Oh, I understand now, sir.
Right? So it
Yes.
closes the contact, which then turns on the timer. And the
Okay,
timer counts down the 200 milliseconds, 300 milliseconds.
okay, I understand, sir.
One more quick question, sir.
Yeah,
Sorry.
man, go ahead.
Yeah, so when you initiate T2 and T3 down here, after that time elapsed, for example, with T2, the contact here below Z1 would close. When T2 ends, the one that
When
is
T2, when 300 milliseconds pass, this contact closes. So you always make the distinction in these diagrams between the coil and the contact. So the timer, the T2 timer, it has a contact. Those are where the contacts are. This is coming straight from the relay. If the fault is on zone 1, this closes and this is energized with this deliberate timer delay. All right. Remember the example I gave with the fire stations? Please don't tell me you forgot it, because I thought that was an excellent.
We remember, sir. That was last year.
All right. So Z1 is the closest fire station. Z2 next to it, Z3 further away. Good. So if the closest station does not, it gets a call, it gets a call, but it realizes it's not a zone 1. If it's a zone 1, it would have instantaneously opened the circuit. But if the fault is in zone 2, and I hope you understand that we're not talking about one fault causing all of this to happen. All right? If the fault is a zone 1 fault, Z1 will close. No argument. All right? If the fault is a zone 2, yes, the zone 2 contact will close. I mean, all of them will close, but if it's a zone 2, it allows time to pass and then it clears the fault. What the missing link here, students, and in fairness, you know, we're going to have to go in detail, is that you will not fully appreciate the operation until we now bring in the communication mechanism. Yes, because the relay will not trip simply because it sees zone 1. There will have to be a handshake from the other end of the line to confirm that it's really on zone on the line. But don't worry, that's the part that, you know, as I said, that's the exciting part. All right, how will you get to that? But just take it for now. Zone 1, instantaneous. Zone 2, timer. Zone 3, longer timer. All right? And as each timer times out, then their contacts will close and therefore close the trip circuit. All right? Then we have differential relays. And, you know, we have spoken about this one. Looks at generators, transformers, bus bars. That's where we find most of the use. And if we're looking at a generator, looking at one coil, we're just looking at what's flowing in, what's leaving. If the two are equal, we're fine. All right? So that's a basic principle for your differential. What we will look at, you know, is your high impedance differential. In other words, we said before that the fault current, regardless of where the fault is, it's going to have to be supplied by your generators and, you know, motors on the system, etc. So you will have what we refer to as through faults. And this may be best, well, let me use a generator. You have a through fault. What that means is that the fault is not on the unit that is being protected by the differential relay. Yeah? But the fault current is passing through that protected device. Make sense? It may be, since we know that the fault current originates from the generator, it may be a little difficult to think it through. Let's use a transformer. The transformer is connecting systems of different voltages, right? That's what it does. A fault does not necessarily have to be on the, well, a fault outside of the transformer. The transformer cannot decide that it will not allow the fault current to pass through. Of course, if the current is going to exceed the operating maximum operating current of the transformer, then the overcurrent protection for the transformer will operate, because you can pass more current than the coils can handle, than the windings can handle. We agree on that? Do we agree on that?
Yes, sir.
Yes, sir.
Good. However, by passing that large current through the transformer, you run the risk of saturating CTs on either side. If you do that, then the differential system is going to interpret that as a fault existing on the transformer. And so we will have to go through a process where we try and determine what is the maximum possible current that can pass through this transformer. And how do we mitigate against that confusion in the differential system? So we have a current passing. Here we know the differential means that if the current entering is the same current leaving, we're good. We don't have to worry about it. But if there is a difference, then it will energize the operating coil and the relay will operate. Yeah, but we have to bear in mind the true fault concept, where the fault current is going, large fault current passing through the device, but it will not trigger the differential system. All right. Yeah, I think we went through this, so I'm not going to spend much time looking at it. Much of the information is already in your notes. We'll come back to all of these. So I've touched these three relays. I've touched overcurrent. I've touched impedance. And I've touched differential. And differential is something you would have also done in machines. Please tell me yes. Can you look at differential relays for your transformers in machines?
Sir.
Yes, sir.
Yes, good. So at least I got one right. All right. We come back to this, and this is what we were talking about in terms of non-identical CTs and their impact. What we'll do next time is to come back and look at each of these relays in detail and look at the circuitry surrounding them and their use. All right. I think that's enough for tonight. You have a good one. All right.
Okay, sir.
You know what?
Sir, we can't hear you clearly.
I'm saying take this one. That's on the screen. I have 8 minutes. So just take the clip of them on the screen and then we call it.